Good day, everyone. We are Group 5 from BSCS 3A, and we are here to present on the topic of discrete event simulation. In this presentation, we will explore how DES is used to model systems through a sequence of events that occur at specific points in time. To enhance the clarity and engagement of our presentation, we have used various tools including Canva for creating visually appealing slides, VED.io for text-to-speech, and incorporated videos and diagrams to provide a comprehensive understanding of discrete event simulation. Discrete event simulation models real-world processes by representing events and their occurrences over time. Since our class has already covered the basics of DES, this discussion will focus on its application in computer science, demonstrating how DES can help optimize systems by simulating real-world scenarios. One critical application of DES is in cybersecurity, where it helps detect and respond to cyber attacks in real time. Let's explore how DES powers intrusion detection systems, IDS, to analyze threats, manage attack queues, and protect networks from hackers. A cyber attack is like a digital break-in, where a hacker tries to sneak into a system without permission. Imagine someone relentlessly guessing your password, trying every combination until they finally crack it. That's brute force hacking. Or picture a server being bombarded with requests, overwhelmed to the point of collapse. That's a denial of service attack. Then there's the sneaky side of hacking, where attackers trick users into giving up their credentials, often through phishing scams that look legitimate. These tactics are all part of a growing threat landscape, where the stakes are high and the consequences can be devastating. Imagine a bustling city, where every vehicle represents data traveling in and out of a network. Now, picture a security guard stationed at the entrance, scrutinizing each, ensuring only authorized ones pass through. That's exactly what an intrusion detection system, or IDS, does for your computer network. It monitors traffic, analyzing patterns and behaviors to spot anything suspicious. It's not just about blocking intruders. It's about understanding the flow of data, learning from it, and adapting to new tactics. In discrete event simulation, we dive deep into the world of cyber attacks, treating them as a series of discrete events. For example, a hacker launches a series of login attempts, and the intrusion detection system springs into action, flagging this unusual activity. Each failed login is a data point, a distinct event that we can analyze. These events are tracked meticulously, mapping out the attacker's behavior. This allows us to predict their next move and strengthen our defenses. By simulating these scenarios, we can understand the patterns and vulnerabilities in our systems. Like a customer service queue, intrusion detection systems operate on a similar principle. When a serious threat, like a DDoS attack, emerges, it's immediately blocked and dealt with to protect the system. Meanwhile, minor alerts are logged for later review. This prioritization ensures that critical threats are neutralized swiftly, while less urgent issues are not forgotten. It's a smart, efficient way to maintain security. When you try to log in, your request goes straight into a queue for authentication. It's like waiting in line at your favorite coffee shop. If you enter the wrong password, our intrusion detection system, or IDS, logs that failure. Mistakes happen, right? But if you keep trying rapidly, the IDS takes notice and bumps you up to a high-risk queue. Now, if those failed attempts hit a certain threshold, the IDS doesn't just sit back. It kicks into action, delaying or even blocking your IP to thwart potential attacks. This smart queuing system ensures that genuine users can keep trying while brute force attackers are kept at bay, preventing them from ever getting in. It's all about keeping your data safe while allowing real users to access their accounts without unnecessary hassle. In the realm of cybersecurity, discrete event simulation is a game changer. These simulations allow teams to practice their responses to attacks, honing their skills without the risk of actual breaches. Queuing systems play a crucial role here, sorting incoming threats and prioritizing the most dangerous ones. This ensures that the most critical vulnerabilities are addressed first, optimizing response times and resources. Companies like Cloudflare and Akamai leverage these simulations to anticipate and detect attacks before they materialize, effectively staying one step ahead of cybercriminals. Security is one area where queuing is crucial, but it's also essential in cloud computing. Another example of discrete event simulation is cloud-based load balancing simulation. Cloud load balancing is a crucial technology that distributes traffic across multiple cloud servers to prevent any single server from becoming overloaded. This helps reduce latency and avoid system downtime. Let's explore how discrete event simulation models cloud load balancing to ensure efficient traffic distribution and optimal server performance. Cloud load balancing works by routing users to the nearest available server. For example, if a user named Diane in Batangos accesses an application, the system directs her request to the backend servers in that region. As more users join from different locations, additional instances are created in those regions, ensuring seamless scalability without needing to change virtual IP or DNS configurations. As applications expand globally, cloud load balancing continues to optimize traffic. For example, when Lisa from Thailand accesses the application, she is routed to the nearest instances in Thailand. If those servers become overloaded, auto-scaling is triggered, and Lisa is temporarily redirected to other available instances until additional capacity is ready in Thailand, ensuring a smooth user experience. Next up is the advantages of load balancing. First, improved performance. By distributing the burden among several resources, load balancing lessens the strain on each one and enhances system performance as a whole. Second is high availability. By preventing a single point of failure, load balancing offers high availability and fault tolerance to manage server breakdowns. Third one is scalability. In order to manage traffic spikes or shifts in demand, load balancing facilitates the scaling up or down of resources as necessary. And lastly, efficient resource utilization. By ensuring that resources are used effectively, load balancing lowers waste and aids in cost optimization. Moving on to the real-world application of discrete event simulation in cloud-based load balancing. Major cloud providers like Google Cloud, AWS, and Microsoft Azure use discrete event simulation to optimize their load balancing strategies. For example, Google Cloud's Traffic Director uses simulation models to predict traffic surges and pre-allocate resources to avoid server failures. Similarly, AWS Elastic Load Balancer employs simulation-based testing to ensure smooth distribution of traffic across data centers globally. These simulations help companies prevent downtime, improve user experience, and reduce costs by optimizing server utilization before deploying changes in live environments. Just as cloud systems balance computational loads, AI chatbots balance user requests.
Imagine a world where conversations with machines feel as natural as chatting with a friend. That's the magic of AI chatbots. These intelligent programs use natural language processing to understand and respond to human queries in real time. But what happens behind the scenes? Let's explore how discrete event simulation enhances chatbot responsiveness and ensures smooth user interactions. AI chatbots are fascinating in how they handle user inputs. First, they receive your message almost like a digital ear tuning into what you're saying. Then they analyze the intent behind your words. Are you asking a question, seeking help, or just chatting? This step is crucial. It's where the magic begins. Next, the chatbot generates a response tailored to your needs, pulling from a vast database of information. But here's where it gets really interesting. When multiple users send messages at once, the chatbot has to juggle those requests like a pro. It organizes and prioritizes them to ensure everyone gets a quick reply. Without this efficient system, delays can creep in, and that's a recipe for frustration. In the world of AI chatbots, a queuing system is essential. Imagine multiple users firing off questions simultaneously. Our chatbot can't magically handle them all at once. That's where the queuing system comes in, organizing and prioritizing requests to ensure fairness and efficiency. There are different types of queuing systems. First, we have FIFO, or first in, first out, where messages are processed in the order they arrive. Then there's priority-based queuing, which ensures urgent inquiries like technical issues get addressed first. Lastly, load-based distribution helps balance the workload by assigning requests to various chatbot instances. Discrete Event Simulation, or DS, is a powerful tool for optimizing chatbots by modeling interactions as a series of discrete events. Imagine each user message as a time-stamped event, marking crucial stages like when the message is received, how long it takes to process, and when the response is delivered. This simulation allows developers to track these timestamps meticulously, revealing insights into response times and identifying bottlenecks, especially during peak traffic. For instance, simulating 5,000 simultaneous user requests can highlight delays and inefficiencies, enabling developers to predict server loads and fine-tune performance. During peak traffic times, AI chatbots face a real challenge handling a flood of requests from users. This is where discrete event simulation comes into play, allowing developers to test various load management strategies. One effective approach is load balancing, which spreads incoming requests across multiple servers, ensuring no single server gets overwhelmed. Then there's auto-scaling, a game changer that automatically adds computing resources when traffic spikes, keeping everything running smoothly. And let's not forget response prioritization. This technique ensures urgent issues like payment problems are tackled first, while general inquiries wait their turn. Leading AI chatbot systems like ChatGPT, Google Bard, and IBM Watson are revolutionizing how we interact with technology. They leverage discrete event simulation-based optimizations to enhance response times and effectively manage large-scale interactions. Major players like Meta and Microsoft are using sophisticated simulations to rigorously test their chatbot infrastructures. These simulations predict system behavior under heavy traffic, allowing businesses to fine-tune their responses and optimize performance.
Beyond AI chatbots, queuing is also crucial in database systems. Discrete Event Simulation, DES, helps databases handle multiple transactions efficiently. In modern systems, many transactions happen at the same time, so a good queuing system is needed to avoid delays. Without proper management, the system can slow down and perform poorly. A database transaction is not just one action but a series of steps. It starts when a user sends a request, and the system checks access, processes the request, updates the database if needed, and then gives a response. If transactions are not managed well, it can cause slow responses, errors, or system crashes. Queuing systems help organize these transactions so they run smoothly and efficiently. DES works by treating transactions as separate events that happen one after another. Each step, like running a query or saving data, happens at a specific time. By simulating this process, database managers can find problems, test solutions, and improve performance. DES helps them try different ways of handling transactions before applying changes to the real system, reducing risks and making the database run better. When a user submits a request, it joins a queue where the database server processes it. Since many requests can come at once, the system must decide which ones to handle first. Some databases use rules like first come, first served, FCFS, or shortest query first, SQF, to organize these transactions. Multiple transactions run at the same time, they sometimes need the same resources, like memory or data storage. This can cause deadlocks, where two or more transactions are stuck waiting for each other. To fix this, databases use techniques like time limits, deadlock detection, or canceling one transaction to allow the other to continue. By using DES, database managers can test different ways to handle deadlocks and reduce system delays. Databases like MySQL, PostgreSQL, and Oracle use queuing methods to manage multiple transactions. Cloud-based services like AWS RDS and Google Cloud Spanner adjust resources automatically to handle high traffic. Industries like banking and e-commerce use DES to make sure their databases can handle large numbers of transactions without problems. By improving queuing models, companies can make their systems faster and more reliable.
Database transactions are essential for handling online purchases, leading us to our final example. An e-commerce transaction is not just a single action, it's a sequence of events. The process begins when a customer selects an item, adds it to their cart, proceeds to check out, makes a payment, and receives order confirmation. Each step must be processed efficiently to prevent delays, optimize resource allocation, and improve user satisfaction. A slow or inefficient transaction flow can lead to customer frustration and lost sales. Discrete Event Simulation, DES, models e-commerce transactions as a series of discrete events occurring at specific times. These events, such as payment authorization, inventory check, and order fulfillment, are processed in a structured sequence. Each event/click is triggered only when the previous step is completed. For example, order fulfillment begins only after payment is successfully processed. By simulating thousands of transactions, businesses can identify bottlenecks, optimize server capacity, and improve performance. When a customer clicks Buy Now, an event is triggered and enters a queue for payment verification. The system checks payment details through a payment gateway, such as PayPal, Stripe, or a bank processor. To prevent slowdowns, transactions are categorized into different queues. High-priority orders, such as express checkouts, are processed faster, while standard checkouts follow a first-come, first-served approach. DES helps optimize this queuing system to prevent payment delays and failed transactions. Once payment is approved, another event is triggered, order fulfillment. The system checks stock availability, updates inventory, and assigns the order to a warehouse for processing. The final phase of the transaction is shipping and delivery. Logistics partners process orders based on priority and destination. DES helps e-commerce companies predict delivery times, optimize shipping routes, and minimize delays by simulating real. Major e-commerce platforms like Amazon, Shopify, and Alibaba use Discrete Event Simulation, DES, to optimize order processing, prevent bottlenecks, and enhance scalability. For example, Amazon's logistics network uses DES to simulate millions of orders per day, predicting peak demand and ensuring that warehouses and delivery fleets operate efficiently. Alibaba's applies DES in its Singles Day sales event, processing billions of dollars in transactions within hours. By simulating millions of transactions, businesses can analyze peak traffic patterns, prevent server overloads, and ensure a smooth shopping experience for customers worldwide. Discrete Event Simulation, DES, is a fundamental tool that enables businesses and industries to model, analyze, and optimize complex systems. Through the examples presented, we see how DES helps detect and respond to cyber attacks in real time by managing security alerts and intrusion attempts. In cloud computing, it optimizes load balancing, ensuring that traffic is distributed efficiently to prevent server overload. AI chatbots leverage DES to process user queries effectively, prioritizing urgent requests and reducing response times. Similarly, database systems rely on DES to manage transaction queues, prevent deadlocks, and maintain system performance under high demand. Finally, in e-commerce, DES enhances transaction workflows by streamlining payment processing, inventory management, and order fulfillment to create a smooth customer experience. In conclusion, discrete event simulation is not just a theoretical concept. It is a practical and indispensable tool shaping the future of modern technology and business operations. Thank you for watching.